So Arditi is an ARM processor division of ARM, formal verification expert. But I guess you're taking a wider context to that.
Thank you. So good morning, everyone. So I'm going to present the 3 challenges for ARM. First, a quick overview of not about what we sell, because I think everybody knows that we do CPUs and interconnects and other IPs. I will very quickly describe how we do verification. So we mostly do simulation using all the EDA vendor tools. We do simulation at different levels. At the block level, we have test benches, mostly based on constraint random. At top level, we have our architecture test suites and also device test suites, which are more specific to a particular CPU. We also do some RTL versus software model comparisons. We use a lot of emulation, FPGA, and we also do some validation on silicon. That is mostly to boot OS and to run software on that. And also to do what we call sub-testing, which means that we run random tests during a very long time, during weeks and weeks, until perhaps we can find a bug. Formal verification is increasing very fast. I will detail a bit more in the challenges. And we have defined actually our AHAA terminology, which means that we have defined 4 big tasks that we want to achieve for verification. The first one is bug avoidance. We want the designer to design correctly, basically. That means they will avoid doing bugs. Because they are not perfect guys, of course, they will still do some bugs. So we need them to hunt for these bugs. After the hunt is finished, or we think it's finished, we want to assure that there's no bug at all. So this is bug absence. And because everything is imperfect, we can still miss some bugs. So in some cases, we have to do some bug analysis on things that have been found very, very late, perhaps by customers or by us, but after the delivery of the project. So I had the choice between 3 challenges, and I selected the 3 first ones here. So the first one is bug avoidance. What kind of strategies can we apply so that the designers deliver a correct RTL code? So a similar question is basically how to fundamentally design correctly. We have done some experiments using formal. So that means that a designer responsible for coding a block, in parallel of writing this code in his text editor, is also running a formal tool to, as long as he's writing new stuff, he has some question, oh, is it possible that these 2 signals are exclusive or not, something like that. So he quickly writes an assertions and try to prove it in formal. And doing so, we have found that the bugs, we don't have fewer bugs doing that, but the bugs are detected very, very early. And this is important because doing that, we can focus over validation techniques like simulation on more integration tasks and more fundamental bugs, I would say. The validation team will not be annoyed by very stupid typos or stuff like that. So on the bottom here, there are 2 charts. They come from a real project on a graphic IP. And on the left, you can see the distributions of the bug along the time. So the x-axis is the time, and the y-axis is the number of bugs. And on the left, that's for the full IP. And on the right, that's for one block of this graphics CPU. And on that block, bug avoidance technique based on formal was used by the designer. So we can see that we found a lot of bugs also on the right, but they are found much earlier than on the whole project. So here the challenge is more, I would say, psychological or sociological. It's how to push designers to use such techniques. Challenge number 2 is bug hunting. So this is a traditional task for simulation and also emulation FPGA. For simulation, the challenge is, okay, we can always grow our simulation farm. We add new CPUs and we buy more licenses. Okay, that's fine. We can run, every year we can run more and more tests, but is there an end to that? We don't know. For emulation and FPGA, the problem is more on the debugability. So these techniques are very good to find bugs, but software simulation is not able to catch. But when they find a bug, it's very difficult to debug it, to analyze it. So here that's more on the interactivity. The challenge is more on the interactivity and debugability. We are doing bug hunting with Formal 2. So I will not detail some ROI numbers that we got, but on a recent CPU project, we measured the number of bugs found by the different techniques, and we could find that Formal used only 10% of the validation effort. I mean human resources and computing resources also. So with this 10% of the cost, we could find 25% of the bugs. So the ROI of Formal for bug hunting is very good. But the challenge here is the growth is not linear. We cannot say, oh, this is very good. Let's put 20% of the resources for Formal and we will find 50% of the bugs. Unfortunately, that's not true. So the challenge is how can we make that true? We try to do some Formal soak. So running Formal for a very long time, it's not efficient at all. And we lost time doing that, actually. And perhaps we can improve the interaction between Formal and simulation, probably to raise the efficiency of both techniques. For bug hunting, one of the challenges is also how to say we are done. And I think everybody has that question. So of course we measure a lot of coverage, code functional coverage and everything, but we know that we want to achieve 100% coverage and we know that's not enough. So EDA vendors, please give us some useful metrics. And the last challenge is how to ensure bug absence. So after we have done bug hunting and we have not found any bug for weeks and weeks, of course we will not dare to say there is no bug. We know that there still have some bugs. We are not able to catch them, so we can try some bug absence techniques. This is very costly. So in theory, Formal verification is the answer to that challenge. But trying to reach bug absence, that means full proofs in Formal is very costly. I mean, for a human, it's very costly. It's not automatic at all. And moreover, we have many configurations to test. It's not possible to test all of them, even with Formal. So we have to make some choices. And we are seeing more and more projects going into end projects which have strong concerns about safety and reliability. And these are probably areas where we need to focus bug absence because here that's more important to have no bug in the planes rather than in the fault, for example. So again, the deployment of the Formal technology is key, but it's not enough for bug absence. We have seen that it's very costly and we still don't have any answer to that. So these were my challenges. Any questions?
Thank you.